Thanks, Matei. So I have a confession to make. I like shoes a lot. Some people, like my husband, might say I have a shoe problem. But today I'd like to show you that this is really a data problem. This is what shoe shopping looks like. So here's Zappos.com, one of my most frequently visited websites. And one of the first things to notice here is that in women's shoes, there are 34,677 pairs of shoes. That's a lot, which is really exciting for me, but it's also daunting. So how should I go about finding a pair of shoes I like on this website? Fortunately, there are some ways to narrow down my choices. Unfortunately, it looks like this. There are 16 different ways to characterize your shoes, each with tens of values, and these are not mutually exclusive. So unlike configuring, let's say, a data center server with exact specs, searching for shoes is really an inherently visual task, which calls for a more visual experience. And it's possible to provide one. So for example, this website, given a pair of shoes you're interested in currently, recommends a bunch of shoes that are visually similar. And underneath this is some pretty powerful machine learning, very likely powered by deep learning used for image analysis. So the question is, why isn't this sort of more intelligent experience the norm? Or why isn't deep learning everywhere? So as Matei pointed out earlier in his talk, there's a common set of challenges when it comes to applying deep learning to problems. One is that to train a single model can take a lot of compute resources and time. Often on specialized hardware, it can take days, if not weeks. And even if you have those resources, it takes a lot of manually intensive parameter tweaking to create a great model for your task. So these two things combined means it can take months to get a good model for the task at hand. And because deep learning models are complex, it means it requires a lot of often labeled data to train a great model. So deep learning pipeline solves these problems by using the Apache Spark for its elastic scale-out power, using MLlib pipelines API to concisely capture the deep learning workflow for common workflows. And as one of its core features, it offers transfer learning from pre-trained models out of the box, which requires a lot less labeled data or even no labeled data than training your own model from scratch. So today we're going to build a visual recommendation AI like the one we saw earlier, but we're going to do it in 10 minutes with 7 lines of Spark code and 0 labels. So let's go to the demo, please. OK. So here, in this Databricks notebook, we've loaded a data set of women's shoes images. And there are about 34,000 of them, not unlike Zappos. Let's look at what the images look like. OK. So there's a pretty good variety of shoes here, from high-heeled pumps to athletic running shoes, tall boots, summer sandals, ankle boots, and so on. So now, as a data scientist, given a particular pair of shoes, how should I go about finding similar items? One natural algorithm to consider is nearest neighbor. For those who might not be familiar with it, nearest neighbor works by assuming that your data points in the data set lie in a space, a vector space, such that things that are more similar are closer together than things that are not as similar. So this means to find the top k most similar items, you can find top k nearest items in the space. And one interesting fact about nearest neighbor is that it actually requires no labels. It just requires that your data be represented in a reasonable way. So one first thing you can try here then would be to take the the raw images, the image pictures themselves, and try this nearest neighbor algorithm. Right? So here we've also loaded the images as one-dimensional vectors. It just looks like a vector. There's a lot of white background. But another interesting thing about it is, if you look at the shape, each image consists of 500,000 numbers, so it's in a very high dimensional space. So if you've worked with nearest neighbor type of algorithms before, you might be like, is that going to work out okay? We'll see how it works. But also importantly, this means computing the distance between the items can be a non-trivial task. And that's bad because to find the top k most similar items, you need to compute the distance between that given item and everything else in the data set, which can be very expensive. But because we're using MLlib, we're in luck. It provides a very fast approximate nearest neighbor algorithm called locality-sensitive hashing, or LSH. And briefly, this algorithm works by, for each item, finding an approximate neighborhood really quickly using hashing, as you might guess. So that to find the top k nearest neighbors, you only need to search in this approximate neighborhood instead of the entire data set. So let me run this real quick. Okay. Here we've written a little helper function called runLSH. We're going to use an LSH algorithm called bucketed random projection LSH, which essentially just computes the Euclidean distance between the items. After creating the object, we can call approx nearest neighbors with the candidates, which will be all the shoes, key, which is the original shoe. And here we'll find 10 nearest neighbors, or top 10 most similar items. So these are the 4 lines out of the 7 that I promised. So let's look at what happens when we run this on the raw image, the original image. This is the shoe, this is the pair of shoes of interest. And here are the similar items I found. I say they're not horrible. They kind of have the same shape-ish, definitely in the same color space, black and beige. But I started out looking for these sort of airy summer sandals and ended up with furry slippers, which look really comfortable, but not really what I was looking for. So as a data scientist, I look at this and say, this is not quite production ready. All right, so what do? Obviously, we're going to use deep learning. Could we go to the slides back? Okay, cool. To talk about how we're going to use deep learning here today, it's useful to start with the more traditional supervised learning scenario, where we have a deep learning model here, which is a neural network, that takes an image and it outputs a label or a set of labels that describe what's in it. So this particular task is called image classification, and it's a well-known problem, but not a trivial one. Luckily, there's been decades of research that went into this by hundreds of researchers, such that now we have a series of really great models that can do this. And these models have been trained on millions of images, usually on this one data set that has 1,000 categories, including things like pandas and cars and daisies and so on. But the key insight here is that these models have become so sophisticated that the intermediate layers are able to capture higher level concepts about the image, such as these edges, blobs, textures, and even whole objects inside. So what this means is that we can take such a network trained on these millions of images that actually don't really include any shoe-specific information, but we can chop off the top layer that gives you the label, take an intermediate representation, and we'll get what's called an embedding, where now this network takes an image and projects it into a lower dimensional space, such that things that are more similar should be closer together, and things that are not supposed to be similar should end up further away. So now with this applying deep learning, we believe that we have a more semantically meaningful space to work with, which is great news for a nearest neighbor. So let's see how we can do this in code. Deep learning pipelines provides a tool called Deep Image Featurizer, which actually does exactly this. So you can make a Deep Image Featurizer object specifying just the model name. Here we'll use Inception v3. It supports other popular models as well. And when we call transform using this featurizer on the image data, it will output exactly that embedding we just talked about that should be in a more meaningful space. So we're going to run the exact same LSH nearest neighbor algorithm just in that new space. And again, here's the original shoe. And the results are much better. And not only is this now able to find shoes that are basically the same shape with different colors, it's able to capture things like the texture such that it can find shoes that are different styles but have the same detailing, like this crochet detail here. And could you go back to the slides, please? Okay. And just for fun, these are the similar images for the sample set we had before, which I would say are really pretty good. For those non-shoe aficionados, it may not be obvious, but for example, not all tall boots are created equal. They have different boot heights and different detailing. And here, we actually have very similar height boots with this buckle detail around the ankle, which is pretty great that this network can capture that. And we were able to build this in just 10 minutes using the power of Apache Spark for scaling out. We didn't run it here today, actually, but the step to take the images and transform them into the embedding space takes only 10 minutes on Spark. That's why it takes 10 minutes to build this. But it takes 6 hours on a single node Keras workflow, which is the difference between almost an entire day's worth of work versus a coffee break. And we were able to do this in 7 lines of code thanks to the simplicity of MLA pipelines. And we did it with 0 labels by leveraging the power of deep embeddings, which was able to capture these higher level concepts about images, even though this particular model was not at all trained on shoe-specific data. And these elements capture the sort of philosophy behind deep learning pipelines, which aims to make production AIs for common tasks as easy to build as what we saw today. So check out deep learning pipelines. We have a deep dive session at 2 p.m. today. There's a bunch of other tools it offers if you want to create your own model for a very different task, for example. And imagine what deep learning can do for you and try it out. Thank you.